But I'm very pleased indeed to have the opportunity to present the first Royal Aeronautical Society Whittle Lecture. We've got to get some slides on here. I believe that Whittle's pioneering work on the turbojet engine is arguably the most important mechanical engineering work carried out during this century. Certainly, there can be few, if any, in the world whose lives have not been affected by it. It led directly to the availability of long-range, high-speed, high-altitude flight, which we all now take for granted. I suspect most have forgotten the limitations of piston-engined airplanes, and I sometimes have to remind myself when I'm enjoying the 3-hour Concorde flight to New York, which is something I'm going to be doing tomorrow, as a matter of fact, that the first time I flew to the US, it took more than 30 hours, bumping along at 10,000 feet in all the weather in a DC-4, with 2 stops on the way for fuel. Now, that was in 1950, when all airlines were still operating piston-engined airplanes. And it is astonishing to think that the young Frank Whittle had foreseen the requirement for high-altitude, high-speed flight and recognized the limitations of the piston engines in this respect in a paper he had written more than 20 years earlier, at the end of the 1920s. But we were still bumping along at 10,000 feet in piston engines in 1950. His initial thoughts were based on gas turbine-driven ducted propellers, but he soon realized the possibility of a propulsion jet and patented such an engine on the 16th of January 1930. And there is the famous patent. His vision was extraordinary when one considers that this work was being done at a time when everyone else was just still undertaking the design of piston engines, and in fact just starting new designs of piston engines. Henry Royce, for instance, was still alive and was completing the design of the Merlin. Unfortunately, as so often happens in these cases, his vision far outstripped that of the officials. The RAE turned down his proposal, basing their judgment on a 1924 report, which was extremely pessimistic on the possibilities of gas turbine power, mainly because it assumed extremely low component efficiencies. The skepticism was not unique to the United Kingdom. 10 years after the RAE turned it down, and now in 1940, when Whittle had been running the first engine for more than 3 years, and indeed, unknown to anyone else in the Western world, the first jet-powered airplane had actually flown in Germany. At this time, 1940, the Committee on Gas Turbines, appointed by the US National Academy of Science, wrote, "In its present state, and even considering the improvements possible when adopting the higher temperatures proposed for the immediate future, the gas turbine engine can hardly be considered a feasible application for airplanes, mainly because of the difficulty of conforming with the stringent weight requirements imposed by aeronautics." Quite interesting that several years later, when Frank saw this report, he said, "It's a good thing I was too stupid to know this." The first ever gas turbine powered airplane, in fact, the Heinkel 178, as I referred to a few moments ago, flew in August 1939 and was the result of von Hohen's work based on a patent he took out in 1935, which was 5 years after Frank Whittle's patent. Hohen is still alive. Indeed, I talked to him only a few months ago in Washington at the memorial service for Sir Frank, and he's still very lively. And he's on record as saying that had Frank Whittle received the support which he received from the German Reichsluftministerium, Great Britain would have had a jet fighter in service 6 years earlier than it actually achieved. And it's quite interesting to contemplate what difference that might have made to World War II. A. Griffith was one of the people in the RAE who turned down Whittle's original idea in 1930. But in fact, he was a gas turbine enthusiast, but he was a scientist, and he was committed to the concept of axial flow compressors. Whittle, on the other hand, was a practical engineer and clever enough to see that with the current state of technology at that time, particularly with respect to aerodynamics and materials, the simple, rugged centrifugal compressor was the only practical solution. There were, in fact, several parallel lines of work taking place in the late 1930s, and indeed, my own company, Rolls-Royce, was working independently of Frank Whittle on axial flow machines, influenced by Griffith, who had joined the company in the late 1930s. And there were some extraordinary designs. I've shown this one before, but it still amazes me because that was drawn in 1939 at Duffield Bank House, and it's a bypass ratio 5 rear fan contra-rotating device, which is really quite extraordinary that people were drawing those sort of machines at that time. Early in 1940, Stanley Hooker introduced hives to Frank Whittle, and Rolls-Royce from that point on got involved in the program and started making parts. And there's a very interesting story that when Hives first saw the first engine, he said, well, how powerful is it? And they said, well, it's 800 pounds of thrust, and we think we can get it to 1,000. And Hives is reputed to have said, well, that's not enough to pull the skin off a rice pudding. And Hooker, on the back of a cigarette packet, demonstrated that a Spitfire flying at 350 miles an hour with Merlin, the propeller, if you assume 80% efficiency, it was being pulled along by the propeller. The release of propeller was producing about 800 pounds of thrust. And that got home to Hives that here was an extremely high potential machine. And he never lost interest. And of course, 3 years later, the company took over the W2 engine from the Rover company and commenced serious production of the Welland engine for the Meteor. And that's an interesting photograph taken at Barnoldswick in the early days with Sir Frank at the back and a very young-looking Stanley Hooker on this side. And that was Heriot, who ran the Rover factory before Rolls-Royce took it over, in fact stayed on to work for Rolls-Royce. Of course, Hives' deal with Rover was an absolute classic. He literally swapped the Rolls-Royce tank engine factory for the Rover jet engine factory at Barnoldswick. He brought Rolls-Royce by that action into immediate large-scale development and production of centrifugal gas turbines. However, in parallel with all that, the axial flow work had been continuing at Derby, and there were some interesting ideas emerging. And this is a 1945 patent. The work was actually started in 1943, the three-shaft engine. And in fact, there was an accompanying patent for a high bypass ratio. It looks from the drawing to be about 5, single front fan associated with that three-shaft machine. I mean, I guess they were looking at about pressure ratio of 2 on each of those spools. But nevertheless, it is astonishing that at this time, all of this extraordinary work was being done. Of course, it was 25 years later when the company picked up the three-shaft idea, and it has been the basis of the success of Rolls-Royce with the RB211 series. In 1941, the government instructed Whittle to pass the design of the W2 and one of the engines to the United States, and General Electric was selected to develop and manufacture the machine, and they moved extremely rapidly. The first flight of that aircraft, the XB-59, powered by the 2 General Electric engines which you see above it, was in October 1942, and that was only 18 months after the first flight of the Gloucester E-2839. So there was a huge compression in the program at this point. The General Electric and the Americans moved very, very fast. But I mean, even in the time of war, the transfer of Whittle's technology to the United States, I think, must be seen as an extraordinary generous action. The centrifugal machines were developed rapidly by General Electric and by Rolls-Royce. Rolls-Royce produced a 5,000-pound thrust Neen and a scaled-down version, the Derwent 5, which captured the world speed record at more than 600 miles an hour in 1946. That's a photograph of it actually capturing the world speed record, at least I'm told. It is probable that more Neen engines were manufactured than any other gas turbine in history. And interestingly, we're still overhauling them in our factory in Canada. All this time later. It's quite extraordinary. These machines do last a long time. But that's not really the reason that so many were built. Unfortunately, in 1946, Stafford Cripps sold or gave a very small number of Neens and Derwents to Russia, who went on to produce thousands of engines, and all MiGs up to the MiG-17, and several other Russian aircraft, and many MiGs later built in China, were all Neen powered, for which neither the company nor the country received any royalty. There are some estimates that maybe 30,000 engines were produced, or even 40,000. And much later, when we were asked to go to look at engines in Egypt, and Russian engines, would we overhaul them? And our immediate reaction was, hell no. The last thing we wanted to do was try to do Russian engines. when we actually saw the engine, we realized we could do it because it was a Neen. Now, this was in the 1980s. So astonishing, generous offer that was made to the Russians, for which we paid for forever. Rolls-Royce did at least profit from licensing the Neen and the larger Tay to Pratt Whitney. The US Navy showed great interest in the Neen, and they instructed Pratt Whitney to get a license. P&W, of course, were a piston engine manufacturer. They were not in the jet engine business at all at this time. And the first 5,000 engines, jet engines, which Pratt made, were Rolls-Royce engines under license. And they went mainly into the Grumman, Panther, and Cougar aircraft, which saw a great deal of service in the US Navy. So it's an extraordinary thing. All of the big three engine manufacturers of today came into the jet engine from Whittle's engine, either directly or indirectly. They were all have come from that common source. The day of the axial engine was, as originally proposed by Griffiths, did not, of course, arrive immediately. It came quite a lot later, and with great difficulty, through the development of the AJ65, which ultimately became the 10,000-pound thrust Avon early in the 1950s. This was followed very quickly by the first bypass or turbofan engine, finally realizing the idea, which was proposed both by Whittle and Griffith. Whittle proposed a bypass engine in the early 30s, and Griffith, of course, was working on them in the late 30s. So the Conway finally made it. It was the first bypass engine in the world. It was a miserable little bypass ratio of 0.3, but nevertheless it started the path which has led to today's turbofans, and that's the Trent 900, where the bypass ratio is 8.6. So a huge movement from the first of the bypass engines. The rapid progress which has been made in civil transport during the past 50 years as a result of Whittle's pioneering work can be seen from this chart of operating costs against time. And you can see the massive reduction in operating costs from the days of the piston-engined aircraft. This, of course, is not just a function of better fuel efficiency and better reliability, but it's also a function of larger aircraft, which have been made possible by the much higher powers from the gas turbine engine. And you can see that one is looking at something like 300% improvement in fuel per seat. That's a strange diagram, actually, because it's based on the TriStar at 100%. But, I mean, you can see that there's something over 300% improvement over that period of time. If we look at fuel efficiency, and that's rather a fussy chart, over a slightly shorter period, and that's really from the Avon through to modern high bypass ratio turbofans, you can see that there's been a 40% reduction in fuel consumption and a 70% reduction in fuel burn per seat. And this has been achieved mainly, the difference is due to the fact that the improved aircraft aerodynamics and lower weight. But again, massive improvements even from the beginning of the gas turbine engine. And productivity, of course, has increased dramatically over this period. The only serious piston engine civil airplane which we were ever involved in was the Merlin-powered DC-4 called the Argonaut. This carried 40 passengers for 1,600 miles at 240 knots. And by comparison, the Trent-powered 777 carries 305 passengers for 7,400 miles at more than twice that speed. So these things are very, very much more productive. The introduction of the turbojet also revolutionized reliability and life of the aero engine. And if we look at engine removal rates, we've gone all the way back there to the first piston engine we made, the Eagle. In removals per 1,000 hours, you can see that it slowly improved as further generations of piston engine, but the real significant improvements came with the jet engine, and ultimately, of course, we get to third generation, fourth generation turbofans, and it's nearly on the bottom of the scale. And I noticed in a recent edition of Flight, I think it was, that they were talking about the last of the large piston engines, the Wright turbo compound, where it said that one could reasonably expect an engine failure on every Atlantic crossing. And that was not much of an exaggeration. Now, that was a very complicated engine. It was possibly the least reliable piston engine ever manufactured. However, even allowing for that, it's a remarkable change to today's position, where we regularly achieve 10,000 flights between removals with no shutdowns. So one's gone an order of 10,000 to 1 in terms of in-flight failures. The gas turbine, without doubt, started civil aviation as we know it. There was virtually no civil flying that mattered until the early 1950s, and that was the start of first the Comet, and then very quickly afterwards a much more effective, because they were bigger airplanes, the 707 and the DC-8. That chart doesn't show terribly well, although you can see it, the perturbations that have taken place and which have been very damaging to all of us involved in this business. Both the airframe and the engine business have been exceedingly hazardous in spite of that steady growth and the projected growth out to the right at today's date, mainly because of those nasty little apparent 7-year cycles which have occurred. And one hopes that those are not going to occur in the future. But the point is that there are no people in this business or observing this business today who are not at least expecting to see 5% per annum compound growth out through certainly through the next 20 years. And most of this growth has been made possible by improved airplanes, bigger airplanes, better and more reliable engines. Now, how's all this improvement been achieved? From the days of the first turbojet, there's been a huge and steady progressive improvement in pressure ratio, turbine temperature, component efficiency, and bypass ratio. You can see there going back from the Avon on through the latest big turbofans. To give you some scale to that, Whittle's first engine was pressure ratio of 4 to 1. Today's big turbofans, the Trents, are 40 to 1. And it is a remarkable step that's from the beginning of the big turbofans, when we all thought we were going to plateau. I mean, there was a huge improvement there, like 25%. There's been another 15 or 20% improvement in efficiency through better components and through steadily increasing the cycle efficiency of the machine. These advances have been most dramatically employed in high-thrust civil turbofans produced by all three of the manufacturers. My own company has uniquely exploited the original 1945 patent with a family of 3-shaft engines from 40,000 pounds to 100,000 pounds of thrust. And the full advantage of the 3-shaft design, which I'm quite sure they didn't see in 1945, is that it was very short, it's very rigid, we were able to optimize the aerodynamics, and it has been fully realized in these very large engines where we've had a significant weight advantage over the competition simply because of that 3-shaft design, which has taken many, many years to refine to its present state. But gas turbines have developed in many shapes and sizes and power almost every type of flying machine, as can be seen from this chart, which shows the wide variety of machines. That's Rolls-Royce's civil range of engines, 12 machines from as low as 600 horsepower to 100,000 pounds of thrust. And you can see there are turboshafts, there are turboprops, there are engines developed specially for helicopters, there are engines developed specially for other types of vertical lift like the Pegasus, and on up through the big transport engines. Maintaining common technology across a range of engines as wide as that is extremely important, and it is one of the things which we and others are doing as a way of reducing risk and cost, because this is a very risky and costly business, and I'm sure when Frank started this business, he can't have fully realized the full implications for some of the companies involved. And this is a crucial date as far as my own company is concerned, because this is February the 4th. Some people remember February the 4th, 1971. So you get these things wrong, they bite you. And we're doing a tremendous amount of work to make sure that they don't ever bite us again. And one of the things we're able to do here is that if you look at all the turbofans on there, from the little FJ44, 2,000 pounds, up to the Trent, 100,000 pounds, they've all got common fan aerodynamics. And at the bigger sizes, where they're hollow fans, they all use common manufacturing techniques and facilities. And this is very important in reducing costs. Furthermore, the whole family is able to draw on a common advanced engineering program, and the opportunity to interchange components and technology to produce new derivatives at low risk and moderate levels of non-recurring cost is now becoming clearly apparent to us. So the latest machine, the Trent 900, employs a scaled-down Trent 800 core with the 800 fan. That produces a smaller engine of 70,000 to 80,000 pounds thrust, ideally sized for this beast, which is the 3XX, and we very much hope that that machine will be launched, because we, with the Trent 900, have got an almost perfectly adapted sized machine for those big four-engined aeroplanes. But we've also found that we can scale the Trent 800 core a little more and produce an engine using the Trent 700 fan, all the units which exist, to produce an engine of around 55 to 65,000 pounds thrust. That would be very, very good for A340 growth, 767-400s, if any of these things ever happen. And as it's the right aerodynamic size, in fact, to put into our RB211-535, which powers the Boeing 757. So with one core, we could have a new machine which would power 4 different airplanes. I'm stressing this approach of progressive development and technical commonality because cost reduction is a big challenge for the next 10 years, maybe forever. Certainly the biggest challenge we all face in this industry. The ability to produce a series of competitive low-risk derivatives will be an important factor in that. If we now look at gas turbines in the military field, we see that the change from the piston engines has been no less dramatic. You can see from that chart that piston engine, the best of the combat piston engines, had power-weight ratios of around 2. And as we've progressed through the gas turbine era, today's engines, EJ200 Eurofighter engine, around 10-to-1 thrust-weight ratio, and we can see machines for the future which we are working on which can achieve 15-to-1 and maybe ultimately 20-to-1 power-weight ratio. That's very important if one looks at the way the fighter business have gone. They've gone for agile fighters, smaller airplanes, require lower size machines, and you see those are cross-sections of 4 military engines, a SPAE through to the advanced machine which we're working on today, all scaled to the SPAE thrust. They're all the same thrust. And you can see the huge advances that have taken place and why you can build much smaller, lighter, agile fighters with the machines that we're talking around today, the EJ200 and ultimately the advanced military engine. Now, I suspect that Frank Whittle saw some of this wide development which would come from his original great idea. Though I do remember when I showed him the early Trent development, and I should have a picture here of us standing together in front of it in 1968. That was the first Trent prototype engine. He looked around at it, and you see his own machine is sitting down. It doesn't show very clearly to the left. He looked around at it and said, well, I really never expected these things to get this large. And I think he hadn't foreseen all the developments which would come. And I know from talking to him that he didn't see the extensive use of gas turbines in other fields, and which has really become a major business. There is a warship powered by 4 gas turbines which were developed directly from aero engines. And in fact, the exploitation of the gas turbine in other applications has become a major business worldwide. It's brought exciting new opportunities in fields such as warship propulsion, power generation, gas and oil pumping, and these applications have increased the market base over which one can spread the huge research and development costs associated with the aero engine. It's interesting the navies of the world today wouldn't exist in the form they do had it not been for the money which we all spend on aero engines. There's no way the navies were big enough to develop machines such as the machines which power those warships on their own. But from the aero point of view, to have an additional market over which to spread this huge research and development cost, it's been a very, very attractive proposition. It doesn't stay at marine. That's the industrial Trent. For the first time, we've developed an industrial engine literally contemporaneously with the aero engine. And this is a 50 to 60 megawatt machine. It's 42% efficient simple cycle, which is the highest efficiency in the world. And we are now looking at possibilities of intercooling this machine up to maybe 100 megawatts. Now, 100 megawatts in the machine, which would sit on pretty well on that raised portion there, is an astonishing thought. And this is why the gas turbine, its huge power density, has made it so attractive for power generation on rigs, in almost any difficult place like the Arctic or Siberia, where you need huge power and low volume. And the gas turbine is producing that ever more effectively. Another very interesting machine we're working on at the moment, and again flows directly from the aero work, is the WR21. This is actually uses Trent and RB211 and a little bit of TAE rotating machinery. But it's built in a, as you can see, somewhat complex machine, which is intercooled, regenerated, and it's being paid for, I'm pleased to say, by the United States Navy, with the British Navy even the French putting a little in. This machine will provide diesel engine efficiency over a very wide range of power, from very low power up to maximum power. The importance of that is that all warships today have to have two gas turbines, or gas turbine and diesel, one for cruising and the other for sprinting. This machine will do both. It's a perfect example of dual-use technology, because again, that could not have happened without the spin-in from the commercial business to military. It's a perfect example of spin-in. And both spin-in and dual-use technology are going to be very, very much more important in the future. And we're very excited by that machine, which has now run about 600 hours and looks very, very good. That's a heavy gas turbine, which we are also putting aero technology into. These are machines of 150, 250 megawatts. The so-called dash for gas in this country and many other places has been based on this type of gas turbine, mainly in combined cycle. That's with a steam turbine running off the steam generated from the exhaust of the gas turbine. And these are typically 60% overall efficiency. And of course, they depend on the highest gas temperature that you can practically achieve in the gas turbine. So the opportunity to draw on the aero engine technology is obvious. Even more surprising is that we've found that we can use aero designs, and indeed some of the technology from the hollow fan blades, in steam turbines. And that's a Trent hollow fan blade in the front. Behind it is the last stage, low pressure stage of a steam turbine. And we're actually now working on steam turbine blades which are titanium and hollow, and of course going to be much longer, and therefore you can get a much higher expansion ratio. And the result is that we can do a 250 megawatt steam turbine in 2 cylinders instead of 3, which will produce a very, very much lower cost solution to the customer. So this aero technology, all of which comes originally from the ideas of Frank Whittle, is permeating almost everything that every rotating machine that we're involved in the world today. The gas turbine, however, envisaged by Frank Whittle, well, he saw it as the ideal power plant for aircraft. And it has proved to have this much wider application. But where is it going to go in aircraft? Well, clearly development will continue to both higher power, improved efficiency, higher temperatures. But these features will have to be associated with progressively lower manufacturing and operating costs. And what we have here is what we foresee as possibly the next generation of commercial turbofan engines. We do foresee that it will be turbofans of moderately increased bypass ratio, maybe 8, 9, 10. We're at 8 now, but 9 or 10. But we see pressure ratios approaching 60 to 1, and turbine entry temperatures may be another 350 degrees centigrade higher than today's engine. So we're talking about now huge steps, 40 to 1 to 60 to 1 pressure ratio, and yet higher temperatures. Now, such a machine would have a fuel consumption about 15% better than the engines which typically drive 747s today. It will have fewer compression stages. It will use I can't say this without another drink, integrally bladed discs. And through the use of low-cost designs and manufacturing methods, could have a manufacturing cost approaching half that of today's machines. Cost is going to be the dominant factor. It's clear to most of us that both first cost and operating cost of airframes and engines have to be reduced if the full potential growth in the civil market is to be exploited. Similarly, if you look at the latest military aircraft programs, such as the Joint Strike Fighter in the United States, low acquisition cost and low operating cost is a major program requirement. So this is the area where most of the exciting work is going to take place in the next decade. Now, part of that, of course, reduction in lead time is important, and we've made a lot of progress in that, but more will have to come. 10 years ago, it used to take us 5 years from the beginning of a design to certification. We did the Trent program in around 39 months from the beginning of design to certification, and the latest Trent derivatives, like the 900 or maybe smaller machines, we're targeting to get to 30 to 32 months. And I think that is achievable. In future, more of the engine will be designed and manufactured and supported by the suppliers. We shall certainly be looking for suppliers to share in the research and development cost. And they will increasingly become partners in the total project. They'll share all the risks, but also all the rewards. Electronic data exchange will become increasingly important, allowing us to maximize the team working between customers and airlines and defense forces. Airframe manufacturers and suppliers will all be working together through electronic connection. And that will lead to better specifications and, again, to lower cost. One is often asked if turbofans can be replaced by some other form of machine. I think not, though I guess if fuel prices were to increase dramatically, there might conceivably be a case for very high bypass ratio open rotor machines, as some people envisaged a few years ago. For civil aircraft, clearly, they wouldn't have military applications. Though there are many problems associated with such devices, and I must say in Rolls-Royce we take quite a lot of convincing that the job could not be done with ducted fans. Now, the ducted fan might take some interesting and exotic forms, and that's one that is a possibility with, and now you see why I said that about Griffith's work in 1940 at Duffield Bank House, because that's a rear-mounted contra-rotating fan, which he was drawing in 1940. Now, there are people in this audience who come from the airframe industry, and most people in the airframe industry, when they see that, tell you go away, because it's a great idea for an engine, but it's very difficult to put into an airplane. But it does have some great advantages from an engine point of view, because once you take away the fan and the shaft down the middle, you can bring the diameters in, you can have smaller compressors, and they're lighter and more efficient. But it is tough to put it in an airplane. But maybe that's one of the way things will develop. I personally believe, I don't think there's another engineer in Rolls-Royce who supports me, but I think it may be a case for the use of heat exchangers in aero design. And the reason I say that is we've made quite dramatic progress in heat exchanger design. And these are industrial units that are based on the hollow fan technology which we have. And to give you an idea, on some of the rigs in the North Sea, we've now got these things in operation. And they are typically 80% lighter and 90% smaller than the equivalent in steel or in conventional manufacturing methods. Now, if we can get those a little smaller and a little lighter, why couldn't you use them on aero engines? And I think there may be an opportunity for us to cool the cooling air. That would be quite powerful. Intercool the compression stages, or even regenerate the engine, but that's much more difficult. You saw how big that regenerator was on the marine engine. It was bigger than the rest of the engine. But cooling the cooling air and cooling the compression stages may be on. Another important issue could be a breakthrough in materials, in particular reinforced ceramics. It is conceivable that one might foresee a gas turbine that had no internal cooling air. And if we could do that, we could eliminate the parasitic loss associated with the cooling air, and that would improve efficiency by maybe another 5%, maybe a little more. However, the move to ceramics in the hot end is more likely to be focused on non-structural parts, initially anyway. And we learnt this lesson with carbon composites applied to the high-fuel fan in the original RB211. The hollow titanium fan turned out to be a much better solution for the fan, but carbon composites are now used widely in the nacelle and other static structural parts. So out there is the possibility, I think, of an all-composite ceramic gas turbine. If we could ever achieve that, it would be very cheap, it would be very efficient, and it would probably open up the automotive market to gas turbines. So there'd be a whole new market available to us. I have to say that so far there's no sign of any material becoming available which would make hot-end structural parts capable of working without cooling air. We're a long, long way from it. But there's a lot of work going on. Now, one of the last things I ever talked to Frank Whittle about was supersonics. And as many of you in this room know, he continued to be very enthusiastic about the supersonic airplane, and in particular the possibility of a second-generation SST. He quite rightly pointed out that the technology is available today, probably for Mach 2.4, 6,000 miles, 250 passengers, so you can get backwards and forwards across the Pacific. The problem is the very high non-recurring costs associated with such a machine. There have been lots of estimates, and I don't know whether they're right or not, but one starts at $20 billion, and you probably go up from there, maybe $30 billion. We're certainly talking about a completely new engine, which has to be variable cycle, a machine that will act as a turbofan at takeoff for noise reasons, and then a turbojet at supersonic cruise. It's got to have a very advanced combustion system, which reduces NOx. No one quite knows what the effect of NOx is at altitude, at a very high altitude. And these machines will be so productive. If they go backwards and forwards across the Pacific twice a day, there's not a market for many of them. Let's say there's a market for 100. How do you amortize $30 billion over 100 airplanes and have a price that anybody in the world could afford to buy? So I think it's likely to be a political problem. There would only be one airplane type, obviously. So it would require the United States, Europe, Russia, Japan, all to work together. It's quite tough to see how that will be achieved. And at the end of that, you've still got the issue of the sonic boom, which there is no way around. So whilst I find it difficult to believe that there will not be a second generation SST, because it will be the first time in the history of mankind that we've not taken the next step in speed, all the way from crawling to Concorde. But nevertheless, it is difficult to see the commercial case. NASA, as you probably know, is spending about $2 billion a year on technology development. But they're saying there couldn't be an aircraft launch before 2020. And then no one's addressing the issue of the boom. Now, the forecast growth in revenue passenger miles in civil air transport, as I said earlier, is 5% per annum compound. And that leads for a requirement in the next 20 years of 18,000 new aircraft. That's 60% to satisfy growth, and about around 40% to satisfy the replacement of existing old airplanes. If I'm correct in what I'm saying, that there'll be no SST, at least during that period, or second generation SST, all of these new airplanes will be subsonic. Many will be twins. They'll have to get very big because it will be necessary to go on reducing seat mile costs. So the big subsonic engine market looks very good to us. And we believe that, in fact, we class big engines as anything more than 40,000 pounds of thrust. We believe that more than half of these 18,000 airplanes will require engines of greater than 40,000 pounds of thrust, high bypass ratio turbofans. And for the Trent family alone, we are foreseeing a 20-year revenue stream approaching $40 billion US. At the moment, we've acquired about $5.5 to $6 billion worth of business with the Trent family. So we think we can see fairly clear lines of development for the whole industry during the next 20 years. And indeed, if we look at the next 10 years as far as we're concerned, it's quite easy for me to say pretty well everything we're going to do we've already planned or committed, which is, I guess, a surprising thing, but it shows up the long-term nature of this business. However, whilst I'm standing here saying this, there may be another Frank Whittle out there somewhere. And I don't think we should ever rule out the possibility that if there is someone out there with an idea, he could make us all look like the piston engine people of the 1930s. And the idea might, like Whittle's machine, change the lives of all of us forever. Thank you very much.